Hello there, geometers. I'm so happy that we can be together, quote unquote. Again, happy Friday to you. Your warm up today involves getting that notebook out and doing what we do every day. Finding a page without questions, write those questions. Find a page without a summary, write that summary. Make sure your summary is the answer to the essential question. Pause and get that business done. Now it's time to set up your new note page, getting started on the lesson. Your essential question today is, how can you translate a figure in a coordinate plane? The topic is translations. The topic goes at the top of the page. The essential question goes right underneath it. And then you're drawing lines, so you create a place for questions, for notes, and a summary at the bottom. When you're done with that, you're going to flip back to that table of contents, write translations, write a page number, and then come on back to this video. All right, so quick review. What are transformations? Transformations are ways of describing movement. Geometric transformations are a specific type of movement, and they've broken it down. Geometers of the past have broken it down into four specific types of transformation. You have translations, you have reflections, you have rotations, and you have dilations. And these by themselves, or a combination of them, describe all types of movement. And in the last lesson, you explored where that you can find those places in the real world, and hopefully you found some places that were surprising and different. Well, as I'm making this video, you haven't done that assignment yet, so I can't wait to see what you do. The thing about math is that it's really hard to see it happening in the real world. And so what I hope is that hopefully this class will help you see that the geometry that you are studying lives all around you all the time. And that really nice way to kind of enjoy math a lot more, seeing that it actually is out there. So we are going to be talking specifically, let me go back. We are going to be talking specifically today about translations. We're going to take that idea and we're going to talk about all the details of it. And then as we move forward, we'll be talking about the other three. So today we're talking translations. So there's some very important things words that we use when we're talking about transformations in general. And those words are preimage, image, and prime. This is good stuff to get in your notes, and don't forget to write diagrams in your notes as well. It can be really helpful. So when we talk about when something moves from one place to another, we have to be able to tell the difference between the starting point and the ending point. And so we call, in geometry, the starting point where something starts, the place where it exists before it moves, the preimage. The preimage is the object before it moves. And it could translate, it could rotate, it could dilate, but the preimage is where it started. And then it moves to its image. That's the ending point. That's where the object after transformation. So we can tell the difference between the two. We have the preimage and we have the image. One is the starting place, the preimage, and the ending place, the image. Now this word prime is actually a fancy word for just writing kind of like a little exclamation, not exclamation point, like a little, what is that called? Apostrophe. So let's take a look at this drawing now, because I think showing you an example is going to be the best way to describe what a prime is. So if we have this segment, and let's call this blue segment AB, we can see from the arrows in this diagram that segment AB is the preimage. The blue segment is the preimage because that's where this object started. And then what that arrow tells us is that it moves over here to this red segment, and that is the image, the object after transformation. But it started out being called segment AB, and we want to be able to tell that it moved to another place, but it's still AB. We want to be able to tell that it moved, though. And so what we do is we add on these little apostrophes, and they're called prime. And so it's segment AB is the preimage, and segment AB prime is the image. Okay? So when you have an object after it has been transformed, it'll have those little primes on it. And so AB turns into AB prime. Okay? You know, PQ would turn into PQ prime. And let's see, Optimus would turn into Optimus prime. Best joke of the year. Sorry, it doesn't get better than that. Anyway, moving on. So now we're going to dig into translations. So a translation is when something just goes from one place to another. It just moves along a plane. A translation is a movement in a plane from one place to another. Translation is like when you're walking. You're just moving along. You're not turning, you're just going in a straight line, translating, going from one place to the other. When things translate, they translate in what's called vectors. When we move in a vector, that describes the motion of our translation. So this diagram here shows a vector. Now it looks like a ray, and so we have to be really careful that we know it is a vector. A vector is a way of showing a translation. It shows both the direction and how far. And how far can be called its magnitude. A vector shows how far something has gone and the direction in which it went. So it shows two things at the same time. Now, vectors are broken up into parts. The first part where something starts, its image would be the initial point. And in our figure, the initial point is P. And then it goes to a terminal point, which is where it ends. And in our figure, that would be Q. And when we indicate vector PQ, we can't draw it like this, even though that's what it looks like, because it's not a ray. It's a description of movement. It's not really an object. And so we can still write our PQ because it has a beginning and an end, but now we just do the top part of an arrow. So if you just see the top part of an arrow, that is a vector describing movement. It's not a ray. Now our horizontal component, since this thing moves, we have to be able to describe how it moves. And really, if you want to travel from P to Q on a coordinate plane, you're essentially going 5 units to the right and 3 units up. And so our horizontal component would be all of the movement that this vector has along the x-axis. So our horizontal component is the movement along the x-axis. And then our vertical component is how far does this thing go up and down, and so we can say the movement along the y-axis. And then when we take these two ideas, we call it, and we put it together, We call it component form, and it has its own notation as well. We'll have our horizontal and our vertical component. In other words, how far it moves in the x direction, how far it moves in the y direction, but we don't want to wrap it up with parentheses. Usually that's what we see when we see x's and y's together, parentheses. But this is not a point, it's actually a vector. And so we're not going to use parentheses here. Math is very specific, and we use different things to describe, different symbols to describe different things. Component form of a vector actually has those guys right there. Okay? So, when things translate, they're moving from place to place. As they move, they can be described by a vector. A vector shows both the direction that something went and how far it went, or its magnitude. Vectors have starting points called the initial point. They end at the terminal point, and when you indicate them, when you're writing them, you write them as a ray, you actually write them with a half an arrow, just the top part of an arrow on top. When we describe the movement of vectors, we describe it, how far does it go along the x-axis, and how far does it go along the y-axis. And then we put those together in component form and write it with a couple of pointy bits to show us that we're talking about movement and not a point. So when we talk about a vector moving with both direction and magnitude, I wonder if that seems familiar to you.
Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! With both direction and magnitude. Oh yeah! Oh yeah!
Yeah, that's how vector got his name, y'all. He's named after actual vectors because vectors show direct movement, shows both the direction and the magnitude, how far. All right, so let's practice. In this diagram, hey, my phone's ringing. Who's calling? I don't know. All right, so in this diagram, name the vector and write its component form. So we're going to name this vector, and that's the easy part. We're going to write j and then k because it starts. The initial point is j, and the terminal point is k. But we're not done because we have to put the right symbol, and that correct symbol looks like the top part of an arrow. So that is the name of our vector. Now we're going to write it in component form, and so in order to do that, we need to figure out how far does it travel in the x direction, how far does it travel in the y direction, and that's going to be a matter of counting. So going from j to k, we're traveling this far horizontally or along the x, and this far horizontally in the y, and what we need to do is count that up. So we have 1, 2, 3 units to the right, and 1, 2, 3, 4 units up. Now these are positive numbers because we've moved to in the positive direction both times. And so we start with the x component, which is 3, and then we write our y component, which is 4, and then we put these little braces in, and that is what that vector looks like in component form. If all you got was this component form right here, you could tell, first of all, that it's a vector because it has those pointy bits, and you could tell that it moves 3 units to the right and 4 units up. All right. So, getting into translations, they can be written using a rule. All right, I had to pause there. All right, so translations can also be written using what's called a rule. And if I could find my pen, I'd start writing a rule. So rules look like this. Now, that looks really complicated, and it can be kind of scary. But the thing about math is, once you see something a few times, you kind of understand what they mean, and you get used to it, and it ends up being just fine. So this rule is actually a description of movement. These things right here, this A and this B, they're going to be numbers. And what they're telling you is how far something is moving in the x and y direction, just like a vector does. It's just another way of saying the same thing as a vector would. And so what this rule looks like is what it means is take point x, y, and again, you got some numbers there that you're working with, and move it A places in the x direction, and B places in the y direction. Rules and vector notation are saying the exact same thing, just in different ways. So the best thing to do is kind of get this business done with an example. And so here's another opportunity to use some graph paper. I've thrown this triangle down on some graph paper, and we are going to move it. And the problem says the vertices of triangle ABC are A, which is at 0, 3, B, which is at 2, 4, and C, which is at 1, 0. And we are being asked to translate triangle ABC using the vector 5, negative 1. So what we know about what we have to do with this triangle is we're going to move it 5 to the right and 1 unit down. That's what that vector notation is telling us. We could write a rule. We could rewrite this vector in the form of a rule, and it would look like this. It's going to start with x, y, and an arrow. All rules are going to start with that right there, x, y, and an arrow. And then another parentheses, and then x plus 5 means that we're going to move x 5 places in the positive direction, and then y minus 1 tells us that we're going to move in the y direction 1 place. So we can take this vector and rewrite it as a rule. Both are saying take your points, move them 5 units to the right and 1 unit down. So now we can use that to graph it. And what you do is you just take each vertex and you move it according to the vector or the rule, whichever one you have. So we're going to take A, which lives at 0, 3, and we're going to move it 5 units to the right, 1, 2, 3, 4, 5, and 1 unit down here, and we're going to have a new point. Now, we're not going to call it A, we're going to call it A prime, because we have to indicate that it has been moved, and the prime is what shows us that. And now we can take B and do the same thing. 1, 2, 3, 4, 5 to the right, and 1 unit down, and there is B prime. And now we're going to move C 5 units to the right, 1, 2, 3, oops, I miscounted, 1, 2, 3, 4, 5, and 1 unit down, and there is where C prime lives, and you have successfully translated this triangle. Notice that it hasn't changed size, it hasn't rotated, it hasn't reflected, it's just moved in that plane from one place to another. So I have a little tip for you down at the bottom. If you do this example on graph paper and then just cut out the picture of that graph, you can staple, tape, or glue it into your notes right where you took these notes so you can remember how to do this later. All right. That's it. That's translations for you. Now, if that went really fast and there's a lot to think about in this particular video, you are always more than welcome to go back and review it and make sure your notes are complete. I also include a full set of notes that you just saw in the Google Classroom, and so you can go back and enhance your notes that way. Your practice today is to log into Big Ideas Math and do the assignment. And as I recorded this video, I don't know what the title of it is yet, but I will make sure that you know before you get it. I hope that you're having a great day. It's Friday when you're getting this video, and so I hope you have a great weekend, and we'll do it again on Monday. All right, take care, y'all. Be safe.